So far we've looked at frequency tables and graphs, skewed versus normal distributions. We've also looked at percentiles, interquartile ranges and ranges, mean, median, and mode. Today we're going to look at how we can measure spread through variance and standard deviation. So as you recall from last time, we looked at this table. We're going to fill up variance and standard deviation today. Variance and standard deviation, if you take a look at the equations, they're actually the same. The only difference is one is squared on the left-hand side for variance, and for standard deviation, they move the square over to the other side as a square root. Standard deviation is usually more preferred, and that's because, for example, in a calculation with a data set that's looking at grams, with variance, you might end up with units that's grams squared. Grams squared doesn't really tell us much because we don't really know what that means. So instead, we created a standard deviation. So when we square root that gram squared, we end up with grams. And we understand, we all know what grams mean. That's mass. So in terms of the reliability, because variance and standard deviation takes into account of all the values, all the terms in your data set, that's a non-resistant measure of spread. So any term can affect the standard deviation and also affect the variance. Whereas, when we look at range and interquartile range, there are only two values in the calculation. So that's why in order to measure the spread, it's usually more preferred to use variance and standard deviation rather than range and interquartile range. We're going to take a look at the distribution preferences. In interquartile range and percentiles, we actually prefer skewed because you only have two data points, right? Q3 minus Q1. Whereas in standard deviation, because it takes into account of all the data set, it's better to have a normal distribution in this sense to analyze standard deviation from. That's also, as you all may know, because that way it's symmetrical. And so that data set, because it's non-resistant measure of spread, would not get affected if it's skewed compared to a skewed. So let's take a look at the variance numerator. That big sigma sign, that means the sum of, right? It goes from the ith term. We usually start with term 1, so that's why I equals to 1 to start with, all the way up to n, which is the nth term. xi means the ith term, so if I equals to 1, then that's the first term. If I equals to 2, that's the second term. X bar, as we have defined, means the mean. You square the sum of that, all the terms, in the numerator, and then you divide it by the total number of terms. So if there are 100 terms, then you divide it by 100. Standard deviation, the exact same thing, except you take the square root. Let's take a look at an example. So a library surveys 20 borrowers each day from Monday through Friday. The number of those unsatisfied with the reading materials are 3, 7, 6, 8, and 11. That means on Monday, 3 out of 20 borrowers are unsatisfied with the reading material. On Tuesday, 7 out of 20 are unsatisfied with the material, and so on. We can do a quick calculation. So what we do here is we first, column 1, put in Monday through Friday, so 3, 7, 6, 8, and 11. Figure out the mean, which is adding all the terms up, and because there are 5 terms, you divide it by n, right? Number of total terms, so it's 35 over 5, which gives us 7. With the 7, we then find the second column, and that's 3 minus 7 equals to negative 4, and so forth. So the first column subtract the mean, and then we square it, and that gives us the third column. We sum it all up, and so in the bottom you see that big sigma sign of the third column, and that gives us 34. We can then calculate the standard deviation by taking the square root of 34 over 5, and that gives us 2.61.